This is KBYP on tuned circuits, transmission lines, and antennas. First we'll start with basic Rlc components, the synthesis of reactive networks, Foster's networks, and then jump over to transmission lines and antennas. There are three fundamental quantities in AC electricity, R, L, and C. R has no frequency component. Very important. L, its inductive reactance is 2 pi times frequency times the inductance. Capacitor is the oddball. X sub C is 1 over the inverse of 2 pi times frequency times capacitance. Three cases of being tuned. Series resonance, where X sub L equals X sub C. Series resonance, as we incorrectly say, is replaced by a short. It's not a short because there are voltages swapping back and forth between the two components. The parallel case, or what we call a tank, where there's a high circulating current, see the arrows going back and forth in both directions within a tank. That's also a series circuit, but it's analyzed with current flow instead of voltage. X sub L is also equal to X sub C. The third case is when X sub L is not equal to X sub C. For example, if X sub L inductive reactance is greater than X sub C, we get the condition of X of C is less than plus JXL, which is less than XL. Stop and think about that for a second. It's fairly simple. It's just one is bigger than the other. Okay, networks are made of those components, generally analyzed without resistance. We buy good components, we minimize resistance, which is mostly loss. A network can be approximated as a black box with a port on each side, and very important to notice they are bi-directional. So this baloney about magic tuners making all the reflected power from the antenna go back to the antenna is flat out BS. Networks do not have that magic property, and I mentioned that in the expose on tuners. LC networks are bi-directional, just as these components are bidirectional. They don't care which way they're connected, except for electrolytic capacitors, which are polarity sensitive, but that's not a function of capacitance. That's a function of the dielectric. In a Foster's network, each mesh in the network comprises, in this case, a capacitor, inductor, first mesh C1 and the inductor, the second mesh C2 and the inductor, so on and so forth. Mesh current is a loop. This is analyzed by this inductive reactance, this capacitive reactance in series. What's the total? Putting that in parallel with this inductor, that becomes a total reactance in the series of that capacitor. But the current in this mesh goes through here, down, around, and back. What that leads to is the first mesh there being the same as this, where C1 is divided up into CA, C sub A, and C sub B, where C sub B is down here in this line. Because it's a current in series, the capacitive reactances in series add together. Fairly simple rules. When we zoom out here for dramatic effect, when we go to antennas and transmission lines, that goes out the window. Ain't no longer applying. And this is where transmission lines and antennas get ugly. As before, with a network with meshes and such, this is a theoretical increment of a transmission line where the length is greater than 0, and that should actually be much greater than. Let's fix that. 2 arrows, much greater than 0. And inductance in series, that's the length of wire, an increment of length of wire in the center conductor, which is also, here's the trick, also added in series with the shield inductance, which is why we never put ferrite clamps on a line, because that increases the inductance of that line in a certain area, changes the impedance of that line, and causes an impedance discontinuity and causes an SWR. Don't do that. It's a very bad idea. Hams do it. They have no idea why they do it, and it screws up the transmission line. So this, basically this repeating LC section is what transmission line is. And it's in theory a Foster's network. Down here shows the shield inductance in series. Similar principle to the earlier page, but we're still looking at the transmission line in a stepwise model of a long increment. That's not what it really is. That only applies if a transmission line is so short that it's no longer a transmission line. An inch of RG58 at 1 megahertz is not a transmission line. It's a capacitor. 2 feet maybe. There have been published by experts such as PhDs and college professors different figures of minimum lengths for transmission lines of 1/12 wavelength up to, of course, a whole wavelength or greater. But the lowest figure I've seen is 1/12, and it's conditional. It depends on what's being discussed. The problem is transmission lines have to be analyzed in increments of 0 length, and this is where differential equations and calculus come in. This is a relatively large diagram implying a large increment of length with a discrete inductance and capacitance, but in reality what's happening is that as the delta in voltage in the signal approaches 0, and here's a sine wave with little tiny, very tiny voltage steps, as those increments get smaller and smaller in time, the increment of inductance heads towards 0. I'm sorry, the increment of length heads towards 0. The capacitance and inductance per unit length head towards 0. Capacitive reactance is inverse, so the capacitive reactance heads towards infinity, and the inductive reactance heads towards 0. Well, doesn't that become basically a short circuit? Yes, it does, except for the sum effect of dielectric losses. The energy is propagating through a dielectric. There's going to be some losses, and we know what transmission line losses are. But schematically, instead of this large mesh, as delta L starts approaching 0, come on, focus. Gee, videos. That's going to be difficult. There we go. The increment of length decreases, and imagine it as a circuit becoming smaller and smaller and smaller till it disappears. And that happens as the increment, the step in voltage approaches 0, and through calculus we integrate that. In fact, with antennas and such, we get 3-dimensional integrals in x, y, z, and including time. But this is under the condition in calculus of length approaching 0 and time approaching 0. We get a continuous transmission line with a continuous signal. No current. This is a horrifying fundamental mistake in antennas and transmission lines, to assume that they are, this previous drawing, to assume that, incorrectly assume that they are discrete elements and there are current flowing through them. In an LC circuit there is current, because incrementally a current causes a electrostatic field that goes back to being a current, becomes a magnetic field, goes back to being a current. The going back part doesn't happen in transmission line. It propagates an electromagnetic wave. And the way to reason that is that radio antenna engineering says, and other books, other PhD level books say that electromagnetic fields can be conveyed by a single conductor. And there is no path for current in a single conductor. And realize that electromagnetic fields can be propagated through space, and there is nothing whatsoever in space to conduct electricity. So that is the basic of networks as they start approaching transmission lines and antennas.